Dear all, you are welcome in this Al-Khwarizmi Applied Mathematics webinar session. It is my pleasure today to introduce Yuzaburo Nakano from Yokohama National University, Japan. Nakano is currently a first-year PhD student at Yokohama National University, Japan, working under the supervision of Professor Masato Takei. His research focuses on probability theory with particular interest in the elephant random walk. The talk today has titled Takagi-van der Waerden functions via elephant random walks, remembering the very recent past. And please, you can start, Nakano.
Okay, thank you, Professor Akechi, for kind introduction, and I'd like to thank you for inviting me today's webinar. Okay, today I'm talking about a certain variation of elephant random walks, which is called elephant random walks, remembering the very recent past, and its connections to Takagi-van der Waerden functions. Today's talk is based on joint work with Masato Takei, Yokohama National University, and published paper of this. So let me introduce what is the Takagi-van der Waerden functions. Okay. D of x denote the distance from x to its nearest integer. D of x on the unit interval is such this figure, like a triangular pulse with height 1/2. And then we also consider d of rkx, and this is increasing the frequency to r to the k on the unit interval. The r is a great integer greater than 2. Then, scaled by r to the k and summation infinite sum over k from 0 to infinity, then we gained fr for every x. Then fr is called the Takagi-van der Waerden functions. The fr is continuous but nowhere differentiable. F2 is introduced by Takagi, 1933, and F10 is firstly studied independently, van der Waerden, 1930. Two figure is the graph of F2 and F3. And these two figure heavily depends on the parity of R. And the first part of my talk, what is the difference of this physically feature of these functions?
Sorry, the figure for F4, for example, it looks like F2.
F2, yes.
For F4, the graph of F4 of X, it is similar
F4
to F2 or not?
This is yes, similar.
Similar.
If R is even, the feature of the graphical the feature of this function is similar.
Okay.
But yes, it differs from depending on the parity of R.
Okay. Thank you.
Okay, FR is the Takagi-van der Waerden functions, and psi k is defined by the term of summations. And psi k defined d of rkx divided by r to the k. So FR is nowhere differentiable, but we are interested in how the modulus of continuity of these functions. For non-zero h, we can find the unique integer m of h such that absolute h is between 1 over r to the m plus 1 and 1 over r to the m. As k is less than m of h, if and only if r to the k absolute h is less than 1. Therefore, by the Lipschitz continuity of psi k, we can evaluate the increments of psi k is such that if k is less than m of h, this increments is less than absolute h. And k is greater than m of h, this increments is bounded by r to the minus k. And therefore, we can evaluate f of the increments of fr by this, such like this. And upper bound is absolute h log r of 1 over absolute h plus some constant times absolute h.
Sorry, I have a question.
Yes.
You affirm that for all h not equal to 0, there exists an integer m such that h is between these two values. But if
Yes.
I choose h, for example, equal to 4,
4.
And r equal to,
Yes.
I cannot obtain this value, no?
H equal 4. Yes. H is need to be sufficiently small.
Okay, very small. Okay.
Such that less than 1 over r.
Okay.
For example, yes.
Okay.
And from these calculations, for fixed h, for fixed x, we have this increments of fr is evaluate this inequality. The the increments of f divided h log r of 1 over 3 to h, and limit soup of this term is between -1 and 1. This is the evaluation of all fixed x. But ignoring the but set of modulus of continuity, we can obtain the following estimate. This is the first part of our main theorems. We obtain the increments of fr is evaluated by CLT type limit theorems and LIL type limit theorems. Increments of
sorry, what do you mean by leb limit? Leb LEB?
Red?
LEB in your theorem.
This is the Lebesgue measure on
Okay. Thank you.
this unit interval.
Okay.
The increments divided by this term and measured by Lebesgue measure converges to the limit distribution functions of standard normal. And increments divided by this term. The limit superior of this term is convergence to 1 for Lebesgue almost everywhere x. And then sigma r is 1. Sigma r square is 1 if r is even, and sigma r square is equals r plus 1 over r minus 1 if r is odd. So the modulus of continuity of fr is depends on the parity of r. This type estimates of modulus of continuity is studied by firstly Kono. He studied R equal to case, and Al-Khwarizmi and Arat is also studying R equal to case. Our result is generalization of them results.
Dr. Nakano, hello?
Yes. Hello. Yes.
Yes, in this slide, so your result, it looks like law of large numbers, okay? Like the central theorem. If you treat x as
this
if you treat x as a
like,
if you treat x as a random variable, uniform
yes,
distribution of 0, 1, it looks like
0, 1.
almost the central limit theorem kind of
Yes,
results,
central limit theorem, and so yes, law of the iterated logarithm result.
Okay.
And we're is what is the difference of the denominator of this fraction? And it is good to see the partial sum of Takagi-van der Waerden functions. The FRN is we define FRN as this partial sum of Takagi-van der Waerden functions. And psi k plus of x is the right-hand derivative of psi k. And LEB denotes the Lebesgue measure on the unit interval. This two figure is of psi 0 and psi 1 for r equal 2 and r equal 3. The right-hand derivative of take value on this divided interval, dividing this unit interval into 2 times rk equal parts, and assign plus minus 1 from left to right. Consider the left picture R equal 2 case. Provided that psi 0 equals plus 1. So this left side of interval. Then psi 1 takes value plus minus 1 with equal probability. And this is the same as psi k, looking at psi k plus and psi k plus 1 plus, psi k plus and psi k plus 1 plus satisfies this conditional distribution. On the other hand, looking at R equals to 3 case, provided that psi 0 plus is plus 1, then psi 1 plus takes value plus 1 with probability 2/3 and takes value -1 with probability 1/3. For general odd R, psi k plus, provided that psi k plus equals +1 or -1, then the probability of psi k plus 1 plus takes +1 or -1 is R plus 1 over 2R. And that means we consider psi k as the random variables on the Lebesgue probability space. Basically, omega equals the unit interval, and B is the polar sigma field on omega. And letting PL 1/2 if L is even, and R plus 1 over 2R if L is odd. Then we can obtain the recursion formula of psi k plus. That means psi k plus 1 plus equals to psi k plus with probability PL, and minus equals to psi k plus with probability 1 minus PL. In fact, psi k plus, the sequence of psi k plus is a stationary Markov chain on this Lebesgue probability space. And if R is odd, PR is 1/2, then psi k plus is random variables. Psi k plus takes in value ±1. Then the right-hand derivative of FRN plus the termwise derivative forms a random walks on this Lebesgue probability space. And what is this process? And it is good to see this process as a elephant random walks. The elephant random walks is a discrete time nearest neighbor stochastic process on the integers with its whole or restricted history, introduced by Schutz and Trimper in 2004. The formal definition is as follows. X1 is the first step of this elephant random walk. X1 equals +1 with probability Q, and moves to left X1 equals -1. This means elephant moves left with probability 1 minus Q. And let beta n is independent family of random variables, taking value in 1 to n, which is called memory variables. And then the n plus 1 step of elephant is defined as x beta n with probability p, and minus x beta n with probability 1 minus p. And our partial sums of xk forms elephant random walk with memory parameter p. If beta n is uniformly distributed 1 to n, then Tn is original elephant random walk introduced by Schutz and Trimper. And looking at the recursion form of psi k plus, psi n plus 1 plus equals psi n plus and or with probability PR, psi n plus 1 plus equals minus psi n plus with probability 1 minus PR. Looking at this recursion, we find that if Rn plus is elephant on the walk, remembering the very recent past. That means taking beta n is n, then elephant on the walk, this taking beta, if beta is n, then Frn plus is elephant on the walk. Remembering the present step, and with probability PR, that moves to the selected step, and with probability 1 minus PR, moves to opposite steps. Okay, next, we are considering the limit theorems of elephant on the walk, remembering the very recent past. Tn denotes elephant on the walk, remembering the very recent past, with parameter p. We introduce Tn as elephant on the walk, but Tn is also known as the correlated random walk. And correlated random walks, limit theorems for correlated random walks are studied by many authors. Letting sigma square is equals to p over 1 minus p, where p is between 0 and 1. Then we have the limit theorems for Tn and CLT and LIL. Tn by sigma and square root of n, convergence to n distribution at the standard normal. And Tn divided by 6 sigma and 2n log n square. This term, limit supremum of this term convergence almost surely to 1. These theorems proved by Allard and Goodstadt-Müller and Konno. Allard and Goodstadt-Müller uses uniformly mixing property of S elephant on the walks. And Konno is found this elephant on the walk is related to quantum works. And the calculation of quantum works, applying calculation of quantum works, and he gained these limit theorems.
Excuse me, Dr. Nakano, what do you mean by diffusive?
Diffusive.
Yes.
Diffusive means divided by square root of n converges to the standard normal. This square denominator of this scaling order. The original elephant on the works, for the original elephant on the works, the limit theorems is different depending on how strong memory parameter. But elephant on the work, remembering the very recent past, is diffusive, no matter how memory is strong. And letting m of h is log r of 1 over absolute h floor, then the increments of the functions can be well approximated by h times this elephant on the walk at time mh. We also consider the generalization of Takagi-van der Waerden functions. Let Wk is a sequence satisfying divided Rk divided by Rk, and Wk by Rk is absolutely convergence. Then TRW defined as this summation exists for all x in the unit interval. For this condition, looking at these conditions, we can find TRW is continuous. But depending on the weight Wk, the differential property of TRW differs. And for example, the smoothness is the problem. Continuous function fx is said to be smooth in the sense of Sigmund if the second order difference is small order h for fixed x. Then Kono proved that T2wx is smooth if and only if T2w is a parabola. This means once we know T2w is smooth, then T2w must be a second continuously differentiable. For example, taking wk as 2 to the minus k, then T2wx is converges to this parabola. And this is the second part of our main results. Suppose that wk satisfies dividing by r to the k, then absolutely convergent. We obtain the complete classification of differential property of TRW. If Wk is square summable, then TRW is absolutely continuous, and with its derivative is the term-wise derivative. If Rk is not square summable and converges to 0, then TRW is not differentiable almost everywhere, but differentiable on a set of continuum cardinality. And if Wk does not converges to 0, then TRW is nowhere differentiable. The Takagi-van der Waerden functions are the third case. In the case of r equals 2, these results are shown by Kono. And in the case r is even, these results are shown by Ferreira-Gomez-Gill and Ferreira-Gomez-Gill-Laurent. As the original Takagi-van der Waerden function is related to the elephant on the morgue, remembering the very recent past. And weighted version of the Takagi-van der Waerden function is also related to weighted version of elephant on the morgue, remembering the very recent past. And first, we consider the independent case. We consider harmonic series. The harmonic series diverges, but alternating sign, this series converges to log 2. And we also consider the series with random signs, Rk over k and summation over k. And this random harmonic series converges with probability 1, where Rk is a Rademacher series. And the question is, for a real sequence Ak, does sigma n converges or diverge? And the answer is Ak is not square summable, then sigma n does not converge, and oscillating minus infinity from minus infinity to plus infinity with probability 1. On the other hand, Ak is square summable, then sigma n converges to a real number with probability 1. This result goes back to Rademacher and Hinchin-Kolmogorov. Regarding Rk as a step of the simple random walk, then sigma n can also be seen as a simple random walk with variable step lengths. And analogous of this simple random walk with variable step lengths, we consider elephant random walk, remembering the very recent past, with variable step lengths. And say Sn. The convergence problem of Sn is also proved in our paper. Suppose the P memory parameter is between 0 and 1. And then Ak, the weight is square summable, then Sn converges with probability 1 and in L2. If Ak is not square summable, then Sn diverges almost surely.
But in the first case, we have to assume that xk has a finite second moment. No? The step.
Yes, xk is, step is the finite second moment. So compared with simple random walks, the convergence criterion is the same as memory rest case. This means the convergence criterion is the same as simple random walk case. And let me add for the original elephant random walk case, beta n taking value, beta n is uniformly distributed 1 to n. An original elephant random walk case, taking Ak is k to the minus gamma, gamma is positive, then even if Ak is square summable, the original elephant random walk may diverge. This result is based on my another paper. And this figure is classification of long-time behavior of the polynomiality gang step, elephant random walk with polynomiality gang steps. Okay, we have less time, but let me jump into the proof of limit theorems for elephant random walk, remembering the very recent past. And Tn denote elephant random walk. Here, where xk is a Markov chain with its transition matrix of this, and satisfying the initial distribution is stationary. And then for A of this event and B in this event, the conditional probability of B given A is bounded by 2p minus 1 to m by 2. And then we can find that xk is a phi mixing sequence. And Tn is a sum of phi mixing sequence of random variables. So applying the limit theorems for phi mixing sequence and stationary sequence, we can gain the limit theorems for Tn. For example, we can apply Blink's-Ley results and Stout results. And we'll consider the weighted version of elephant on the work. We prove this theorem. And the first part of this theorem is the Burke can be proved by Burke-Holder type inequality. First, using the Yoshihara inequality, we can evaluate the fourth moment of Sn minus Sm can be this, bounded by this. And using the phi mixing conditions. And also by the Moritz inequality, we can evaluate the maximum of SL minus Sm. The fourth moment of maximum of SL minus Sm can be bounded by this term.
And what is the sequence A, An, Am?
An, yeah. Sorry.
Okay.
Capital sorry. An is the square sum of AK, weighted sequence. And Sn is the weighted sum of xk.
Okay. So here you use martingale properties?
No. Sn is
Locality.
not martingale.
We can obtain some martingale from Sn. Okay.
Yeah.
Okay.
No.
Okay, thank you.
It depends on the coefficient An, I think, being martingale or not possible.
Martingale, we can use by phi mixing conditions, we can obtain this result.
Okay.
So we don't use martingale property.
Okay.
This inequality implies the L2 converges, and for maximum fourth moment of maxima, L2 converges implies almost sure convergence. And the second part is follows from this lemma. The Sn minus Sm, the second moment of Sn minus Sm can be bounded above and below by weight ak square, the sum of ak square with some coefficients. And supposing Sn converges with probability 1, then the left-hand side of this inequality implies Sn minus Sm is bounded. The probability of Sn minus Sm is bounded is close to 1. Then the left-hand side of this inequality implies AK is square summable. That means AK is not square summable. Then the probability of Sn convergence is less than 1. And by the tail triviality for a phi mixing sequence, we can find the probability of Sn convergence is 0. Okay, we are turning the proof of modulus of continuity. As I said, the increments of this function is approximated by Elephant and Mork, remembering the very recent past. More precisely, we can obtain this approximation. For h between 0 and 1 over r, and letting m of h of this, then increments of fr is approximated by h times Elephant and Mork at time mh plus the small order term. Once we prove this lemma, applying the limit theorems for S sub mh of x, we can obtain the central limit theorems and evolve the iterative logarithm for the increments of fr. This is a proof sketch of the main theorems. Okay, future work is we mentioned the future work of these two future works, and we can obtain the differential property of this weighted version of Takagi-van der Waerden functions, but we cannot obtain the modulus of continuity of FRA. And also, I am wondering, we can prove a more strong result such that almost sure invariance principles for FRX. That means the increments of FR is approximated by h times sigma r some coefficients, and Brownian motion at time mh. mh is defined by this, and plus some error time. Once we can prove this almost sure invariance principle, the central limit theorems and rho of the iterative logarithm for increments of Takagi-van der Waerden functions immediately follows. And they are future works for today's talk. Okay, that's all for my talk today. Thank you.
Thank you, Yuzaburo, for this talk, for this subject. Are there some questions, please?
Yes, can I have a question?
Yes, Carlo, yes.
Let me first thank Professor for the excellent talk, Professor Nakano. I really appreciate his work. I'm wondering if there are some connections with ergodic theory. In other words, do you see some interactions between van der Waerden type results and ergodic or dynamical system approach? Can you see some connection between these functions and your estimate with some dynamical systems?
Yes. Back to the definition of the Takagi-van der Waerden functions. D of x is the distance from x to its nearest integer. But d of x is also the fractional part of x. So d of rkx is a fractional part of rk times x. So the sequence d of rkx, according to k, forms a dynamical system on the unit interval. So yes,
They
we can
also
regard
remind me the Weierstrass functions with sinus is similar to sinus and power and some special powers. Did you study the connection? Maybe there are some relations between them with Weierstrass.
yes, Weierstrass.
As far I remember, it is a sinus, and then there are some powers with some special indexes. So
Yes,
they look very similar. Also, the plots on your function R3, yes, F3 looks very similar to Weierstrass function.
Yes.
Probably you can extend very easily your results to Weierstrass series, a Weierstrass nowhere differentiable function. So you could do very easily. You have all stuff, all material. The tool you have already done.
Yes, I am wondering. I can extend the result to Weierstrass functions. Yes. To be honest, the results of Weierstrass functions that exist and investigation of the modulus of continuity for Weierstrass functions are studied by many authors.
Yeah. Okay.
Yes.
But I see very close to your van der Waerden functions. They are very close.
Yes, very close.
Okay. I will study because long time ago I also was working on these functions. So it's really interesting for me. Thanks a lot. I will research your paper and I will study this subject. It's very interesting. Thanks a lot. And thanks also Professor Rafik for the interesting conference. Thanks a lot.
Thank you for you, Professor Katani.
Thanks.
Are there other questions, please?
Yes, please. I have a question.
Yes, I'm sorry.
Thank you very much for this nice talk. Indeed, I want to know what's the difference between the modification you made in the elephant random walk. It was the IID case. And now you introduced the sequence beta n. So what are the assumptions on beta n? And why do we need beta n?
Beta n is referred as
sorry, Yuzaburo, for the original elephant random walk, the elephant remembers all the past and he chooses one step in the past. But in this case, in the work of Yuzaburo, he chooses only the recent past, the recent step. At time n plus 1, he chooses only step n, and with probability p, he repeats the same step. With probability 1 minus p, he do the opposite step. Okay, so beta n, it is not very useful in this talk, but Yuzaburo, he has introduced beta n just to give some information about the original elephant random walk.
Okay, because indeed it's related to the limiting, to the limit theorem he obtained. Because in case the sequence Tn is still Markovian, such as the case of the IID case, because it's Markovian in that case. If it's Markovian, then the central union theorem is indeed can be observed as the central union theorem for Markov chain. So I want to know whether it's treated as a central union theorem for Markov chains or not. If yes, what are the techniques that you used? Because often the central union theory is very well known in the literature on quantum on Markov chain.
Okay.
It means in your case, is the sequence Tn Markovian or not?
Sequence xn is Markovian.
Yeah, it's
And
abused, but also the sequence Tn in the usual case is Markovian. It is inhomogeneous Markovian. In your case, is it Markovian?
yes.
So the central union theory can be understood as a usual Markov chain central union theory.
Sorry, I copied. In this, yeah.
Tn is
related.
okay, man. Okay.
Sorry, just a related question to Abdul Fattah. The Xn is not Markov, right? Xn, frequent Xn. Because it does not today does not depend only on yesterday. It depends on maybe previous days. Right? Am I understanding right or not? The sequence Xn is not Markovian.
Xn plus 1 depends only on Xn and not on all the past in this talk.
لا
Yes, in this talk.
But the previous depends on beta n. But beta n can be 1, 2, 3, and it does not just depend on yesterday.
Yes, but even in that case, we get a Markovian, an inhomogeneous Markovian, because
yes,
in many cases, the elephant work is considered as non-Markovian. But it's really easy to show that it's Markovian, but inhomogeneous. In the multi-dimensional case, yes, it's not Markovian. But in the one-dimensional case, it's Markovian. Concerning, you mentioned also the works by Kono. I think it's really interesting to make the bridge with quantum random walks, and in that case, maybe new phenomena may appear, given the rich background in the ergodic theory on that algebraic level. That's also interesting direction, maybe that can be investigated.
Okay. Thank you, Abdul Sattar, for these remarks. Interesting remarks. Are there other questions, please?
I have maybe a naive question.
Yes.
Can you please go to first slide, maybe, or second, number 2?
Yes,
okay. Fr of x is a kind of R-adic decomposition, no, of x.
R-adic.
You take a number and you decompose it in the basis R.
Yes, this is all.
And you have unicity of the decomposition, no? We are in this setting, no?
No, this is not the decomposition of Rx. But D of Rkx is the fractional part of Rkx. Then we can divide it by Rk. So
it's the distance from x to the nearest integer.
Yes.
Okay.
From R to the power k, x to the nearest integer.
Yes.
I have a general question. The results strongly depend on whether R is even or odd. Okay. What is the deep reason behind this dichotomy? Why we have this dichotomy? Why the asymptotic changes were with parity of R?
Yes, the reason is the psi plus, the property of psi plus. When R is even, the psi plus is IID Rademacher sequences.
Okay.
But if when R is odd, this psi plus is stationary Markov chain, and that means depending on the present state. And the increments of FR is approximated by this elephant on the work, the sum of psi plus. So the increments of these functions depends on the parity of R. So the limit theorems differs when R is odd or R is even.
Okay. Okay. Are there other questions, please? The localization criterion depends only on summation of a k-square converges or diverges. Why does memory not affect this condition? The memory P, the parameter P. So for all P, if the sequence AK not squares summable, we have divergence for all P.
Yes.
Okay.
For all P, yes.
And in some slides, you have introduced X1 is symmetric Radmacher random. Yes, here.
Yes, here.
We can have another Radmacher random variable not symmetric. Probability X1 equal 1, for example, equal R and not R, Q, and X1 equal -1 equals to 1 minus Q. We change the results, the asymptotic results or not? If we take another Radmacher distribution of X1.
I think
it does not affect the results.
Changing the initial distribution does not affect the limiting behavior of. Sorry. Yes, does not affect this limiting behavior.
Okay. Return to the elephant random walk, and we consider an elephant random walk remembering, for example, the two earliest steps at type n plus 1. It remember step n and step n minus 1. We can obtain some results about your functions here or not?
The CLT and LIL have been obtained by. Sorry, I can't. I forget the.
Okay, no problem.
Name of this. Yes, but have been obtained. Yes, CLT and LIL.
Okay. Some other questions, please. If not, we have to thank again Yuzaburo Nakano for this nice talk, and see you next week with Giovanni Piccati from University of Luxembourg. Thank you very much.